Hey Bulldogs, Chris Bryant, CCIE number 12933 here, and in today's Cisco certification tutorial and video practice exam, we're going to take on link state protocols. In your CCNA studies, you really concentrate on the configuration and troubleshooting of OSPF, and believe me, that's enough. We've got plenty of details there to concern ourselves with. The other major link state protocol, IS to IS, you really run into that configuration in your CCNP exams. But not only do you need to know how to configure and troubleshoot OSPF for the CCNA exam, but you also need to know the overall behavior of link state protocols, particularly when compared to distance vector protocols. So that is what we're going to concentrate on here today with question 1, which of these statements, and always select all that apply with my questions, accurately describes a link state protocol? And we're going to stay here for about 10 seconds on each question. You can always pause the video if you need a little more time, but I like to have plenty of time to give you the answers and explain them to you on live Cisco equipment here at the end. So let's go ahead and move on to question 2. What term is given to a router, an OSPF enabled router, on an OSPF segment that is neither the designated router nor the backup designated router? There's actually a term for that we'll see in one of our OSPF commands. What is that? Let's move on to question 3. Which of these statements accurately describes OSPF? We'll move to the next question. Which of these does not have to match between potential OSPF neighbors in order for an adjacency to actually form? Which one of those do not have to match? And then finally, our last question today, which of these OSPF adjacency states is unique to an NBMA network? Because you know we've got a lot of details to watch out with NBMA, but one of these adjacency states you're only going to see with that particular kind of network. So let's go back to question 1, and then I'll bring the live pod of Cisco equipment up as well to check some of these answers. Now, which of these accurately describes a link state protocol? A does not, because the benefit of link state protocols is that they do not send routing updates at regular intervals. We like that because it takes up less bandwidth and it's one less thing for our routers to have to do. B is actually true because link state protocols will advertise only the changes when a network change occurs instead of an entire collection of links or routes, because the link state protocols actually advertise links rather than the typical routing table we see, say, with the distance vector protocol such as RIP. C is true because we're going to have a database, and you can see that in OSPF with show IP OSPF database, and we do not, as network admins, want to have to work with that because it's a collection of links and it's very difficult to figure out anything from it. I'll actually show it to you here in a minute. What we want is a routing table like the one we're used to. And we're going to have that once the SPF algorithm or the Dijkstra algorithm in OSPF runs against the contents of that database. So C is true. D is false because link state protocols do not advertise full routes and masks. Again, they advertise the state of their links. That's where the name comes from. So let's jump to question 2. What term is given to a router on an OSPF segment that's neither the DR nor the BDR? Well, here's what we call that, and I'll bring the live equipment up here. It's called a DR other, and I have an NBMA network here where router 1 is my hub and 2 and 3 are my spokes. So that's what we expect to see in an NBMA network because we kind of rigged the election so that neither routers 2 or 3 could become the DR or the BDR. So again, whether that's an NBMA segment or a broadcast segment, it doesn't matter. If a router is neither the DR nor the BDR, it is referred to as a DR other. Also, while we're there, let me show you that database command. Actually, no, there's something there I want to show you for the next question. Which of these accurately describes OSPF? A is true because it is purely a link state protocol. The hybrid protocol that B refers to is actually EIGRP. C is true because OSPF does use hello packets to create and maintain adjacencies. D is false. We don't have to manually create them, especially always, because we have other things to do and OSPF will handle that for us. E is true because OSPF will send hello packets at different intervals depending on what kind of segment you're on. On a broadcast segment, such as Ethernet, they go out every 10 seconds. On a non-broadcast segment such as NBMA, because that's what the NB stands for, non-broadcast, it's going to be every 30 seconds. And then finally, which of these does not have to match between potential OSPF neighbors? The process number. B is false because OSPF doesn't use an autonomous system number, and potential neighbors are going to have to agree on what hello and dead timers they're using on that particular segment. But A is the one that does not have to match. That's our process number. Now here is our final question, and I'll show you that database as well in just a moment. Which of these is unique to an NBMA network? It's actually the one that you see here, because I ran show IP OSPF neighbor while the adjacencies were forming. You could see NA, and that meant that our adjacencies had not yet formed, and it's attempt. You're only going to see that in NBMA networks because that refers to a unicast hello packet. That's another one of those things we have to do for an NBMA network when you're running OSPF on it. And you can see then it went to full, and that's what we want. But you will see attempt early on in an NBMA configuration. You can see here there where the adjacencies then went from loading to full, and again, that's what we expect to see. That's what we want to see. Let me show you that database one more time as well, and this is a very small database. I haven't put too many routes in here yet on this particular network. This is a very tiny database, but I wanted to show you this because this is what the link state database actually looks like. And you and I as network admins, we don't want to go in here and try to figure out routes. We want to run show IP route or show IP route OSPF to see them. So again, show IP OSPF database will show you the actual database full of links, and then the Dijkstra or SPF algorithm, whichever you want to call it, runs against the contents of that database, and that's where we get our OSPF routing table from. Thanks for taking today's OSPF video practice exam. We've got well over 100 of those on our YouTube channel as well as the Bulldog blog. Thanks again, and I'm Chris Bryant, CCIE number 12933.